Hi everyone, this is a presentation about graph neural networks. My name is Triet. Right now I'm an undergraduate majoring in aerospace engineer at UCLI. So before I begin with all of this, so first let me give some background about this AI and machine learning and neural networks, stuff like that. So first, on the big pictures, you have it's called artificial intelligence. It's very early stage. So basically, you're applying this technology of robotics and coding and stuff like that to solve a problem, human problem. That's mainly called, artificial intelligence. You use intelligence from uh, machine and stuff like that. And after that, a smaller subset inside artificial intelligence, you have machine learning, in which it's self-explanatory, but machine that can learn from a past experience. So that's the definition of this smaller subset. Let's say it doesn't have to be machine. It doesn't have to be like neural networks and all the advanced AI we have right now. It can be a simple chatbot that can brute force learn from a user input experience. Like it's pretty. It doesn't have to be the high advanced technique. And then finally, we have deep learning, where the actual things you're using today is from deep learning, is where we actually use neural networks and just mimic the human brain, neurons, that kind of stuff. So we're interested more in like develop techniques and knowledge in this deep learning model. So a very famous phenomena example inside deep learning where it's a neural networks where you have an input layer where you input your data, an output layer when you're interested in the output of that model. Then you have also hidden layers with a lot of neurons, and then they are connected by weight, and then you add biases, activation functions, that kind of things. And normally, you can train this model to get a very good prediction of the data you inputted. So that's also standard, pretty much standard neural networks that everyone probably know. Then after the deep neural networks, if you modify this neural networks a little bit, so specifically the middle uh, layer, that's called layer by the way. So the middle layer, if you structure the layer in a way that the input dimension is big, and then you decrease the dimension a little bit until the middle layer is called latent space, is very small dimension, and then you increase it again into a higher dimension in the output data. This concept is called an autoencoder. And so this concept autoencoded also you can see them repeatedly in many machine model. And why I think itself is useful in some case. It's mostly applied, I see in the other models. It's like a smaller, just a smaller application that you're going to see in a lot of spaces. And the concept have an encoder, right, where you encode the data into a different dimension. Then when you solve it and everything else, when you solve it finished, you decode it with a decoder, the output. So from this autoencoder, you can uh, further advance it and modify a little bit to get two other models. Right, you have a variation autoencoder in which everything is the same as the autoencoder, the structures. Just the middle one is instead of a fixed node, a fixed variable embedded values, you chain it into a distribution, a probability distribution. And with this probability distribution, is a generative model. You can generate a lot of image and different things with this model. Then another generative model come from also not exactly the autoencoder, but you can see some pattern in here. It's a GANs model where you can develop some very realistic image and products from these neural networks. So it's technically competing between the two AI, right? So you have these neural networks and this neural networks, and they're fighting each other, and they become better and better. And the better they become, the better the generator is, which is the generated part that we're interested in to generate very realistic face in this case. So you can see the generator is having the decoder structures, right? Smaller to very big dimensions, small to very big dimension. And the discriminator, on the other hand, you can see it kind of off the encoder with very big dimension to a smaller dimension. Then there's some normal neural networks put into here. That's the GANs model. And there's another model. I don't think I went over much on this playlist yet. but this is a sequential model. So in some case, the data is not specifically this way. Sometimes the input dimension is not fixed in this case, right? Sometimes the input dimension is changed a lot. So this example is a stock market. Every day pass, you have a new value to input, right? So that's the input dimension is increase over time. It's a vary in the input dimension. Also, this is also another sequential data where this is Gemini from Google, by the way, similar to ChatGPT. So the prompt I input into the chat can vary a lot. So it's not, it's not just one. I can put in one word, two words, or a very long word depending on what I'm doing. And it take all the kind of input and give me the output. Right? So the input I mentioned vary a lot. For special model, this is a recurrent neural networks. I don't think I covered this much, but technically you have a lot of sequential model. In the end, you have this transformer model, which in the paper, attention is all you need. And this is very important model that is the core of ChatGPT. It's very famous right now in 2024. And also Gemini from Google, right? This is from OpenAI. So the two most famous sequential model that I know of from this model. And then, okay, so this is the big pictures that I have in mind so far, at least before I look into graph neural networks. And when I think about graph neural networks, I was wondering where does it's going to be fit in this pictures? Where is graph neural networks in these big pictures? When I thought about it for a while, and I think it's going to fit like right here. So it's going to be even before deep neural networks and before this sequential, this is recurrent neural networks. And why do I put this in this way? Because if you look at this graph structures, if it's a little specialized, okay? If it's a little specialized, right? If you rearrange this node in a specific way and connect them in a specific way, you're gonna get deep neural networks. And similarly, if you rearrange them, you just have a one line graph, you get this recurrent neural networks, right? So this deep neural networks of this is just a special type of graph neural networks. That's to my understanding. And so now today that we're looking at graph neural networks, it's not just this special case, right? We're learning more a general case of graph neural networks. Yeah. So that's the background. And here's the outline of this main today presentation / lectures. So first I'm going to talk about graph neural networks applications. So in order to talk about this application, I'm going to give some basic vocabularies. Then we can talk from this vocabularies, you can understand more about this application. And then the second part, which is I think probably the most boring part and most technical part is going to be how it works. We'll talk about the tree approach, message passing, propagation. This is like tree approach of how it works. It's the same thing, but just different way of saying it. And lastly, I'll talk about future works that I'm going to do for this graph neural networks. Okay. So firstly, I'm going to talk about some basic vocabularies. So this is a graph. You've probably seen them a few times before, but you have so this circle thing is a node, similar to neuron in regular neural networks. There's also another word for them is vertex. They use them interchangeably, and then the connection between the node are called edge or link. Right? So you connect the node, it's going to be called edge. And then for each edge, you have either undirected edge or directed edge in the red over here. So if undirected edge, this node can pass information to this node, and this node can pass the information back to this node. So it's two-way, both ways. For directed edge, it's going to be one-way information. So this node can pass information to this node, but you cannot do otherwise. You can pass this node to information to this node. Okay. And lastly, you have graph, which is if you have a bunch of this thing, it's called graph. So it's a combination of different nodes and a lot of edge together. So you combine them, it's called graph. And that's the basic vocabulary we're working on. From this vocabulary, you can see there's three objectives, and therefore that's the three predictions we're going to do. First, we're going to do a node level prediction. Right? So we're going to predict the node. Example is you classify the node like pink and purple. Pink is someone smoke, and purple is someone who doesn't smoke. then you have this node in, you want to see if it's pink or purple. The question is this person smoke, right? Or you have an edge prediction. So you predict, does this edge exist or not? One example is the next Netflix video. I'm going to cover this a little later in the application. And finally, we have a graph level prediction, which is predict the whole graph. So this one predict if this whole graph is molecular structures is a suitable drug. That's an example of it. Yeah. So now we have some basic vocabularies. I can give you some real life applications that you can see pretty regularly in real life. So first, with the node level prediction, let's predict the node. The one phenomena application is going to be fraud detection. In this case, also determine if an article is fake or real. So you have a bunch of articles. You can this is digitalize them, embedding them, convert them to machine language, and then you make a graph out of it. And then from this graph structures, you train it a little bit, and then it can classify if this node is red or green, and how much red is it, how much green is it, which red being the fake articles, and the green node is the real articles. And then you also set up allocation can be used also in fraud detection in financial service, where you can use the same method of both, but just apply in a different application. You can see it's pretty much applicable everywhere. The next one, you have the edge level predictions, where you can predict the link or edge between the nodes. So this is an example from uh, watch the next movie link. So you have two similar users. If this user watch this three movies, so this movie, and this movie, and the right user only watched the first two movies, right? So they are very similar, and very likely the link between the third movie at the bottom and this user on the right is very likely. So it's going to recommend that movie to the right user. Another one you can see is Google Maps. So map is technically a graph, and you can put the dot between them and make a graph from it, and then you can predict the link or the edge, right, which is the pathway inside a Google Map. Is this what's the color of it? So how fast you're gonna move? What's the time it's gonna take? Is it red? It's gonna be take longer. Green is gonna be faster to move in that segment of the graph. The link, the information about the link between the node. There's also the thing about differentiate graph from normal neural networks is interested in the link and not just the node. And the last one is the graph level prediction. So again, with the Google Map kind of things, you can see it also can create a graph for you, create a pathway from one location to the other location, which make up a graph from a lot of possible graph to generate a possible fastest graph for you. That's one application. Another application is in drug discovery. So if you have the drug is just a bunch of molecular structures, and if you can use put in input in molecular structures and predict its behavior from these molecular structures, which is a graph level thing, then it's pretty good um, way to reduce the amount of possible combination of molecular structures that you can test out for drug. And I think they have a very big success here already with a lot of papers about it on the drug side. I think it's one of the main things that make graph networks like popular. Yeah. So that's the application of graph neural networks. So next part, I'm going to talk about message passing, which is probably the most important words of this lectures. And if this is the one thing you're gonna try to understand in this video or this lectures, like if you can forget about all this stuff, you can forget about any of this, any of the future works, but definitely understand message passing, this part. Yeah, I have a start here, please. uh, yeah, steal this from one video on YouTube, but anyways, this is very good animation to show you how message passing work. Right, so try to understand this to start on. Again, emphasize that. So you have this bunch again, the vocabulary. You have this note, so one note, two note, three note, four note, six note, seven note. You have one, two, three, four, five, six, seven, eight, nine. So like nine nodes here, right? And then between the node, you can see the link between them. Like one link, two link, three link, four, five, six, seven, eight links are edge interchangeably. Then message passing, in this case, is that you can see you have one node over here. It's gonna send information to the neighboring node. So not this node over here, but the neighboring node that's connected with the edge. So this one sends it this, and this. Right? And if everyone doing this, you're gonna see that not only you sending it, but this person also not only just send, but also receive note from this person, and this person. And also some link, if you notice, is undirected link or edge, right? So this edge is undirected, so information from this to this, and information going from this to this node. Why this link is directed a link or directed edge, where information only flow from this node to this node over here. Right? So this going to this way, and it doesn't go the other way around. So that's the directed edge. Message passing, uh, you receive information from your neighboring node, right? While giving up your information to. You combine all of them with your own information. You after the time agree after a time step, you change your information. You keep repeating to several rounds. That's the technique of message passing. Okay. And that's one way to look at how graph network works. There's two different propagation, aggregation, message passing there. They're quite a similar concept. I'm just going to go over the other two ways. It's technically similar to message passing. I'm just looking at it a different perspective to give you a more overall view of it. So this way of looking at it is from a more neural networks way. So in neural networks, you keep seeing this layer and layer. So it's a force with brute force change this into neural networks. You can see a similar pattern here. So you start with this yellow node over here. After one aggregation, right, so one time step, so you propagate, it's going to pull information from this node, and this node. So all the neighboring nodes that's connected with it, right? So you have the one, two, three over here. And then after this, the second aggregate, uh, each node going to take from the neighboring node. Okay? So this node getting from this blue node and yellow node. Right? So this node getting from blue node and yellow node. Similarly, this node getting from the yellow node and this node getting from the blue node. This node getting from the yellow node and this node getting from the blue node. Then this node going to get from the green node and not the yellow node because this directed um, edge. So it only flow information only flow from yellow to blue, but it doesn't flow the other way. And then another perspective to see look at it is from a mathematical perspective, where this is the graph. You have h I of t plus one. So the next step of h is the node itself, equal to a learnable function. Inside the function, you have, and then you're going to see the AITW. This is the node itself, right? So the information of the node itself is important, plus a linear combination of all the neighboring node, so Hj of t, that you just say a changeable weight, a learnable weight that train the neural network. But Hj of t is the all the neighboring node around that node you're interested in. Okay? So that's the three perspective you can get from how the GNN graph neural network works. And then for future works, I plan to read this paper from Google, a gentle introduction to graph neural networks, which I think furthermore that a message passing method, where in this one you only see the information that you know are traded among the nodes, but not the edge or graph level. So this paper cover more in depth about how you train the edge and graph level, not just the node level prediction. And also there's this course that I plan to watch over. It looks very interesting and very in detail technical content. of machine learning with graph from Stanford. Totally open source and free on YouTube. Yeah, that's the end of this presentation.